All right, welcome to Space Hackers. This is April 3rd, 2025. This is Eric Veal, and tonight's guest is Marcia Drake. And so don't have a long preamble before Marcia's talk, but just a couple kind of quick reminders for people that might not know about Space Data Hackers. So we're a part of Space Northwest, and tonight's talk is called From Maps to Mars, the Evolution of GIS and Space Analytics. And I'm Eric Veal on the right there. And then my buddy Mike Doyle, he is the president of Space Northwest and has helped to organize this group and create the little subgroup here for Space Data Hackers. We're a technical community for people that like data or people that like apps and tools and software and engineering around space, or trying to make sense of space. Just a quick little pause on our purpose here, but we're a community of people who love data and space. We explore data sets captured from space, share knowledge, and build skills for putting data to use to solve problems for our communities. I won't read the whole thing, but that's kind of our purpose there. So welcome. Just again, like quick little welcomes here from me. Do a little introduction to Marcia and just hand it off to her. But please find us on Meetup. We're at just meetup.com. You can Google us and find Space Hackers, probably the first thing that comes up. If you'd like to find out more about Space Northwest, you can find it on the membership page within spacenorthwest.org. And just kind of different things that Space Northwest is looking for, volunteer and that kind of help. So info at Space Northwest is another resource for you. And if you have ideas for upcoming talks, it was through Mike Doyle that we found Marcia, and those guys have known each other for sounds like about 4 years now, just got that fact. And so if you would like to speak, if you have ideas of speakers or ideas of topics, please reach out to me. I'd be happy to understand what the idea could be and hopefully get that produced. And really, without further ado, I think, Marcia, I'd like to just kind of hand it off to you. But Marcia is our speaker tonight, and I'll just hand it off. Welcome.
Great, thank you. And let me see can I share my screen now?
Make sure you can. I think you got it now. Yep.
1 second, and I'll pull this up. And... Okay, so my focus tonight is really a deep dive into my personal journey of learning GIS and also a little bit about the evolution of how GIS has advanced over time, as well as some of the underlying principles behind GIS that I think might give people some ideas for how to use it in different ways and how to ask different questions, how to think differently. And I'm Marcia Drake, and I'm the CEO of EcoHeart Coaching and Consulting. I have over 25 years of experience in government data. I also spent some time at Microsoft Global Security with Pinkerton Investigations. And I've been all over the place. I've spent a lot of time in different state agencies. I've also worked with a number of federal agencies, tribal agencies, and partnerships. And I've worn all hats in data. So I realized, wow, I started out as a fingerprint expert, which I'll touch on in a moment, but I've also been a data scientist. I've managed databases. I've done, of course, GIS, but I've also learned as a trained transportation analyst, trained crime and intelligence analyst, data quality, data management, all things data, all the way on up to a chief data officer. So tonight, what we're going to do is we're going to talk about GIS. And I realize that some of you in the audience may be experts. You may have created amazing things with GIS. Some of you may even have more knowledge than I do around GIS. But nevertheless, I'm going to share some basics for those who may not have had quite as bit of knowledge around what it is. And then we'll get into some of the more technical things. So for those of you who are more advanced. I'll also be looking to you to maybe share some things later about your experience and some great things that you've done with GIS. So, what is GIS and why does it matter? Well, here I've got a definition where GIS, it's a system that captures, stores, analyzes, manages, and visualizes geospatial data. There's a lot of other definitions out there, but for this talk, we're going to kind of stick with that one. And the importance of spatial data in decision making, we're going to talk about that today, as well as the power of GIS in solving complex geographically distributed problems. And the world has a lot of data to explore, and this is where it gets exciting. I think maps are one of my favorite ways to look at data. So my journey in GIS development, I was thinking about it, and it's like, I started out when I was in college as we call it a dactographic morphologist, doing fingerprint imaging. And at that time, we were taking these fingerprint cards, and we were scanning them into a computerized system so then they could be matched up at a crime scene later. And as part of that process, my job was to not only scan the print in, but to mark the key features of that print on the screen, on the computer, so that later, when it was matching up prints, it could more easily find a match. What I realized is that we were using an XY grid at the time. And how many of you remember back in the days of algebra when you were using the XY coordinates and you had to do all that math to calculate that? Well, that was a grid. And some of these underlying principles, it's really what they were using at the time. And I had this aha during my progression into GIS that the fundamentals underlying GIS mapping also have a very similar concept. So it's all a grid. And as we get into this, when you start playing with different layers of data in GIS, that grid and remembering it becomes very important because you can actually perform math within the grid. So just a little fun fact there that wanted to share. So after that time, of course, I entered into state service, and one of my first jobs right out of school was to handle all of the traffic fatalities for the state of Washington. And during that time, I did early work with NHTSA, the crash test people, National Highway Traffic Safety Administration, and U.S. Department of Transportation, as part of that national database that tracks all collisions that are fatal throughout the United States and uses that data for making your cars better, for making better roadways, and all kinds of things. And during that time, we had some limitations of traditional data analysis, and there was really a need for more precise and actionable insights. And early on, the folks at NHTSA were like, hey, wouldn't it be great if we could start mapping collisions? There were a few people out there that had started doing that with handheld devices, but it really wasn't in the databases at that time. And we thought, well, we could try that. However, not everybody had the handheld devices. So the next step was, whoa, let's build a geolocation tool so that the analysts can manually mark where those collisions are happening, or maybe the officer in the field who's investigating a traffic collision can actually mark that on the map. So we began development around a geolocation tool. And at that time, I was sitting as chair of the U.S. Department of Transportation National Information Technology Advisory Board for that database, the FARS database. And we actually developed a geolocation tool. And during that time, We also found a lot of very interesting considerations that I think still hold true in maps today. One of them was, of course, legal and personal data considerations. We didn't know if what we were putting on the map would be a liability. And in fact, in Washington state, we found, yes, there were some things that we had to put protections in place so that we would be able to share these maps with the public. So that was one consideration, but also the accuracy of the tool. The map, every map is a little bit different. And depending on how it's calibrated, the curvature of the earth, the particular method that's being used, things may or may not line up quite right. The way that the map had been drawn, the way that other landmarks had been measured, they all played a role in how accurate we could get, as well as satellite accuracy. And if any of you have ever played with GIS or maybe one of those handheld devices, well, even on your phone today, there are times when you might be a little out of range or your map may be slightly off, and the next thing you know, it says that you're supposed to be at the Burger King parking lot, but instead, maybe you're at the ferry dock. I've been there. Um, so, as you look at some of these little nuances, it's very important whenever you are working with maps, working with GIS data, to validate that your base map, that everything is accurate before you draw conclusions, because a lot of times it might be plus or minus, a few feet. Other times it could be a very big difference depending on what map you're using. So that was a huge breakthrough, that we found a way to, for the first time, start to visualize where these collective collisions were happening. And it was something that we envisioned would help with decision making. We could make our roads better. We could actually identify, see it firsthand for the first time where we needed to concentrate our attention. So after I was there, then I went over to the Washington State Patrol and I worked as their head analyst, research person there at the patrol. And I brought GIS mapping to the patrol for the first time in this capacity. And it was there that, and it looks like my slide got something carried over, but in this capacity, what I did is I developed GIS, geospatial maps, started to map all of the Washington state collisions for them, as well as getting a hold of 911 crashes, getting a hold of 911 calls of drunk drivers, reports of drunk drivers, getting a hold of things like bar locations, the roadway layers, of course, looking at other interesting things. I found it all. I even found a layer for roadkill, if you can believe that. And that was kind of interesting when you're considering traffic safety. And of course, we did find some hot spots there as we were, looking for certain types of hazards. But what we were able to do at the patrol was really to put data in action for the first time. So it's one thing to create a map. It's another to actually see something that you can now go out and do something about. And I always talk about the power of data. For the Washington State Patrol, that power of data was about saving lives, ultimately, reducing fatal collisions on the roadways using this information. And spatial analytics really enabled us to see patterns in a different way that we hadn't seen before. We could see where the clusters of drunk driving collisions happen. where speeding collisions happen, where, motorcycle collisions were happening. And it was something that was a great communication tool as well, helping policymakers um, and other people who are involved in making roads safer to take some proactive decisions towards making roads safer. So, part of the lesson here also was around traditional data versus spatial data. And using the example of some of the things that we saw at the patrol, we found a way to actually animate the maps through time and space. Now, that was really revolutionary at the time because we didn't have the tool in the Esri software to do that. We were actually taking screenshots and then feeding it into a video to animate. And 7 days a week, that was a lot of screenshots if you consider 24-hour period, but we did it. And of course, set it to music because you have to do that if you're doing a little mini movie. But what was great about it was for the first time, we were able to see where those DUI collisions were occurring. And you could see through time and space, quiet, quiet, quiet. And then Saturday night, here's the casino area. You start to see the calls of the 911 reports coming in. And then the next thing you start to see is, oh, here's the crashes starting to happen up here. And then, oh, where are the law enforcement? Well, at the time, they were all working in a different part of the county. And when we showed that to them for the first time, they were like, wow, we need to be up there, of course. And so that was really revolutionary in the way that we were able to view this. However, the way that historically in Washington State, a lot of funding for traffic safety was awarded was based on traditional data. And what we found is they had been running numbers for the whole state, the trend lines, and the most common time that a DUI collision would occur was between 3 and 5 p.m. And they were actually putting conditions around some of the emphasis patrols for the officers and said, well, we'll give you this money, but only if you patrol during this hour and this hour. And I actually had one of the troopers there who had looked at these maps. He was up on the peninsula, somewhere up around Port Angeles. And he said, I can tell you, you can give me the money, but I'm going to sit there all night. I'm not going to find anything. And that's because now I'm aware that my collisions are all happening at noon, and it's because of recreational drinking. So what we found is that the reason for the difference, all of those statistics were skewing to Seattle. And Seattle had, roughly about 30% of the population. But it was something that had been accepted. Nobody had questioned it. And people just, it was ingrained in people's heads that between 3 and 5, when the bars close, that's the most dangerous on the roadway. Not true in other parts of the state. So it's always good to question some of those traditional assumptions, some of those traditional statistics. And what is amazing is that when you add the dimension of time and space, things can change. Everything that you know can go out the window. And when you incorporate the where and the when, it gives you a richer understanding of things. So from there, this is an example of some hot spots that were similar to the type of things that we were creating at that time. And the discoveries, as I mentioned, shattered prior assumptions and bias. It helped us gain new insights. And we also learned a bit about linear flow versus space. So another type of technique that you can use as you're looking at data, if you're getting into spatial analytics, is the difference between let's say, the flow of traffic on a roadway or the flow of water in a river. And there are other examples of when you might use that kind of a technique, but it is a little bit different from running something that's going to be in a different kind of a shape, more of a square grid, for example. And as we looked at this, the fun part about Seattle area in particular is there's a lot of water. And I remember, I think it was somebody back in the Midwest had come up with a methodology to predict collisions. And I said, ooh, I'm curious. I want to know all about that. And so I called them up and I started thinking about it and how they were describing the technique. And I said, well, wait a minute. Do you happen to have, or does your model account for a lot of mountains and a lot of water? Because we have both. And it seems like it could potentially skew the data. And I remember there was quiet on the other side of the phone, and they're like, I wouldn't recommend using our our statistics for the Seattle area. It's like, okay, great. That was a bit of information. And so we ended up going to a method where we actually removed some of the water layers from the Seattle area, some of the non-traveled routes to better be able to run some of the spatial analytics. We also did a lot around with the roadways in particular with the linear concept. So just wanted to point that out. It's just another way to kind of think through different types of shapes and data that you might be playing with. And, all in all, just to summarize the story, we had an amazing success with this. In fact, this technique is still in use to a degree at the State Patrol. I'm sure it's evolved even since I've been there and started the program. But we did find that we had a significant impact on our roadways. We reduced collisions, and we had better resource allocation. It increases safety, and it's something that I like to say I'm happy to have been a part of that effort. Again, considering time and space, this is just a quick summary of that. Understanding when and where events occur leads to more actionable insights. Time of day patterns and traffic accidents. And also you can look at seasonal trends in similar ways. So we looked at winter crashes and weather impact, for example. So there's a lot of different time and space types of analytics that you can also do. And you can do this with sustainability data. You can do this with space data. You can do this with so many things, but always consider time and space in your analytics. So then moving from that into descriptive to predictive analytics, as I mentioned a little bit about that prediction, I really wanted to know more about how do we do that. And GIS can be very insightful for understanding what might happen in the future. Of course, any kind of forecasting is always based on what has happened in the past. So you do have to make an assumption that's assuming things are not going to change so dramatically that you wouldn't be able to get an accurate read on it. But for example, what we looked at was predicting areas that were prone to crashes during specific weather conditions or times. And then the role of spatial analytics and data-driven decisions. This is kind of a fuzzy picture of New York State, actually New York Police Department, that was one of the early examples of putting data in action. And Washington State Patrol has a similar type of technique where they're really monitoring maps on a regular basis and the data to make sure that they are working in the right areas, that they're driving those collisions down, and that they're finding issues that exist out there. And now, with the ability to do real time, there's some cool stuff that you can do with all kinds of data. And so thinking about, if you do have a real time dashboard, what does that mean for your decision making? Why would you want to create something real time? What's the purpose behind it? Because when you're looking to put data in action, it's more than just creating a map. I've seen dozens of maps created that really don't go anywhere beyond, ooh, that's pretty. But if you really want to make an impact with things, think about the application and how somebody would use it. So how do we connect that to space data? There is a growing connection, of course, between GIS and space data. And this is also a favorite topic for me. I've loved seeing with the hackathon, for example, some of the projects that people have done. And everything from space weather, satellite, information. I think I saw stuff around moonquakes and moon stuff, Mars mapping, all kinds of stuff that we can look at here. And using the satellite imagery, of course, another favorite thing of mine. And I love this animation here because it does show our beautiful Earth from space. And there is so much now that we're finding that the satellite imagery can give us insight into. I was recently looking at an example of tree coverage and being able to use the GIS satellite imagery to examine that layer and to find changes over time. Again, that time and space factor can be very insightful. And also realizing that every data point that you have in there, you can have other data that lies underneath that data point. So, for example, when I was talking about the collisions, we might have one dot on a map, but that one dot could have hundreds of other data elements attached to it below that. So there's a lot of deeper analysis that you can do with any of this data. And with the tree layer, being able to calculate something like carbon credits becomes possible because, again, it comes back to the math. I mentioned the grid earlier. It's kind of learning how to work with it in that capacity. So we can use this for things like urban development. I mentioned the deforestation, climate stuff. We can also identify risk areas this way. Where is the areas most prone to fire, wildfire, for example? Very useful and meaningful application of the tools. So the role of GIS in space weather predictions. Of course, we've all watched the weatherman on TV or the weather woman talk about, what's coming the next day and watch the beautiful satellite imagery of the hurricanes approaching the coast. But we can also do the same kind of stuff with space weather and look at solar flares. We can look at cosmic radiation. Again, there's probably some of you in this group who have already experimented with that. And as we come to the end of this, if there's any of you who have done some of that work, I would love to hear about it because this is not something that I personally have done yet, but I think it's still very much the same kind of principles underlying the geospatial analytics. So we can also do things like map solar storms to predict effects on power grids. I think being able to connect what's going on in space also with what's going on our planet is very fascinating, and maybe even vice versa, to understand the impact space or our planet is having on space. That's another type of analytics that I don't know how many people have gone down that path, but I find it a great opportunity. Planetary mapping and space exploration. So another advancement of GIS is the fact that now we can also do these 3D layers. We can do um, LiDAR. I mean, there's all kinds of different ways to look at this, and it just brings to life the type of things that we're looking at and adds another layer there of understanding. So, for example, if we're looking at Mars or a planet and we're sending out a rover, um, it can help us to determine some things. Same thing with satellite imagery, being able to detect the height of the terrain, maybe even the presence of water. It's incredibly powerful. Predicting optimal launch times and locations. Again, time and space, which can bring together a whole lot of different kinds of data. Spatial data for planning space missions. GIS to analyze planetary conditions or weather patterns and launch sites. Using GIS to analyze conditions for lunar or Mars missions even. The possibilities here are really endless. And the future of GIS in space data, I think that there's quite a bit more that we can do that is untapped. I have not seen the use of GIS quite like I've expected to over the last few years that I have been involved with it. And I think that a lot of people stop at the simple creation of the visual, and they do not harness its power at that deeper level. And as we start looking at space in particular, oh my goodness, there's so much that we can do. And even the way that that data is integrated with AI for more precise spatial data analytics. Again, I mentioned that each of those data points, when you're putting those layers in, can have a lot of data attached to it. So now that you can take data in and out of maps, you can also feed it into AI and you can put it back in. There's a lot of different possibilities that we can do with learning to utilize the GIS to its full potential. And there's a lot of collaborative platforms that are being developed out there now that allow you to do a little bit of that, maybe even automate some of that. But for those of you who have never really dabbled in GIS, I really encourage you to go and learn some of it. Of course, I went through learning Esri products. There are a lot of different products out there as well. But it is just, it's a lot of fun. And if you've never done it, please give it a try. There's a lot of free trainings out there to dig in. And there's a lot of data now available that even back when I was first learning this, we just didn't have access to. Now there's oceans of data, literally. So conclusion and key takeaways. Again, the power of GIS. So connecting Earth and space. GIS enables smarter decisions by incorporating both time and space. And from improving road safety to monitoring space weather, GIS's power continues to evolve, especially as we start to link it to AI, as we start to link it to things like our Web3 and new technologies coming up, I think we're going to see a lot more activity around this. And a call to action. Space data professionals should embrace GIS for deeper insights into both space exploration and Earth monitoring. And yeah, there are many, many applications there. So key takeaways. I would say learn GIS, ask lots of questions, never say never, explore your patterns, explore your data types, explore spatial analytics, and above all, have fun. And thank you so much.
Thank you, Marcia. So open time for just anybody with questions in a discussion. Is that kind of how you'd like to take it? I think let's at least be open for the next 20 minutes of chit-chatting just about what we learned and what questions we might have for Marcia. And I guess go ahead and just holler out unless somebody wanted to raise their hand or whatever. But I think go ahead and just holler if you have a question, come off mute and let's talk.
Marcia, something you brought up that I found interesting and hadn't really thought about is the effects that Earth might be having on space. And I was pondering that for just a moment, thinking about mainly various types of pollution like satellite debris or signal pollution or something. What else? What other topics in that realm are you thinking about?
Well, one thing that came to my mind is noise. How does sound travel from our planet elsewhere? I think there's I know that we've sent sounds out into space the other way, and we ping objects that way. But what about how noisy are we? And what does it look like from the reverse? I think one of the things I enjoy doing is taking a problem or even something that we've kind of researched and flipping it upside down and just asking the question a little different way. And yeah, we might find something interesting there. I don't know. Maybe somebody's done it.
Having read the Three Body Problem series recently, I think about the noise that we're making in the radio frequencies, and maybe that wasn't such a great idea to begin with.
Well, if there is anybody else out there in the universe, I do wonder what they hear, with all the stuff that goes on our planet. What are they hearing on the other side if they exist? So it's kind of fun to think about.
Any other comments or questions about what we heard?
I could probably
I
keep
think the
going.
comment is, we always talk about space data and we talk about that at the hackathon a lot. And GIS almost never gets mentioned, but a lot of these problems are GIS related problems, right? Taking that data, mapping it onto an area. Not all space data is geospatial, right? There have been NASA challenges that have been around, data related to NASA missions and equipment. But this is a really good backdrop, I think, for folks who are going to be looking at the bulk of the kind of problems that are part of the Space Apps Challenge.
Do we just kind of think of it as additional layers on top of GIS? Is it like just new signals and we're always overlaying it onto some map or not? I don't want to say always, right? But is this kind of the metaphor that we primarily understand as technologists today, as we've used a lot of maps by now, and that there's just additional layers coming from space that we can lay onto GIS and it's just new extensions to the same old pattern?
Yeah, I think my biggest caution, and we're all guilty of this to a degree, but again, we see something beautiful, a map, and we stop there. We don't dig in and ask, how was that map formed? What does that mean? How did it even get created? And I see the same thing happening with AI. there's a lot of people who are really quick to take the algorithms and run it, and they come up with something, but do they really know what it means? Do they really know how the algorithm worked and where that data came from and how it was fed and what questions they're answering? And those are kind of fundamental. I mean, they go back to like statistics 101. Those are, I think, that's the gold, because otherwise we get used to just assuming that it's telling us one thing when there's just a whole world of questions that we could be asking of this information. So yes, the layers are part of this. There are so many different layers that you can bring in for those questions. And one thing that I like to do when I'm playing with maps is I bring in as many cool layers as I can. We used to not have the capability to bring in that many because it would crash the system. Now we can handle a lot of data. So I would encourage you to just get in there and play. And you might find that one layer is cooler than another, and then you start turning off the layers that don't look as good or they're not useful. But yeah, sometimes you can find some good stuff.
I have a bit of a definitional question for the group, if you don't mind. Obviously, not all GIS data, or probably even much of it, is space data, but is it safe to say that any space data, whether it's optical, radar, thermal, or radio frequency that pinpoints to a location on the surface? So let's set aside the atmosphere for a minute, mate. Would all of that be considered GIS data? So if it's something taken from a satellite and it says this temperature Earth at this place is 84 degrees, or the radar bounced off this building here at this time, or this ship here, that would all be considered GIS data, correct? Or no? Anyone know?
I think it is. I don't know if I'm the one supposed to answer. My personal opinion would be, it would seem like that interface that is lat long, right, has to be what GIS is
Okay.
if you have a, in my opinion, right, it's like, I mean, in the early days, wasn't it, I mean, it's all military signal grade originally, and it was X, I can't remember what the radius was or whatever, but it feels to me like the precision of lat long and having two columns in your data set that are lat and long allow you to bind some fact to a map, literally, or to geospace.
That's what I thought. So most space data of the Earth is probably GIS data, whereas the other reverse is not true. Most GIS data does not necessarily come from space.
Well, we could call it geospatial, right? Once that geospatial data is put into a geospatial information system, it's GIS data. That's how I would break it down.
I thought the spatial and geospatial, I didn't know that spatial had to do with space. I thought it was space on, not space, but okay.
Yeah, sometimes I just called it mappable data. I think that's
That's
another way around
too.
it.
I think like the interface from a total pure programming language, you make an object that's called IMappable, and it necessarily has lat long.
Mhm.
And
Okay, this is kind of it's kind of a silly point away, but sometimes these terms are all over the map. And,
nailed
I was
it.
just curious.
Nice.
I would think that if you've got a third dimension, that you're now into a spatial realm, and we argue where space starts and stops anyway, and the atmosphere is fairly continuous in terms of it goes up and just thins more and more and more. So, we're arguing in quite a lot of our meetings and other aerospace stuff is where does it start and stop. So I don't think you're unique in not being sure where it starts and stops. My question might be: are we getting enough resolution in our information? Can we get better resolution from our imagery? Is it a pain point that we're paying a lot to get that resolution, or is everybody getting the information you want?
Resolution just keeps going up, and the price keeps coming down, and its accessibility keeps spreading. I don't remember what kind of resolutions are available now, but it's now this kind of things that were, you know, at national security level not too long ago.
It is part of the mental problem here that we're like binding ourselves to the earth. Like I liked Marcia when you started with the example of thumb kind of as a metaphor of like it is an XY grid and a coordinate this and that. And so it obviously doesn't have to be earth that we're binding to. Like geo doesn't mean earth, it means surface or space per se, the third dimension.
Mhm. Absolutely. Well, and I see Tim's comment in here. Seems like you're working with X, Y, Z or a fixed area. Yes, I think, as we start adding in those other dimensions, we do have those other
Yeah.
aspects. But
Yeah, and I see Daniel had a good one there as well. I think GIS helps tie data to the surface of a 3D object. It's interesting. To the surface, right? And then is Z saying it's subsurface or super surface, like it's in or out of the surface? I have no idea.
And if you're looking at real-time information, I mean, is the data, can you link that real-time into a useful output? Are you getting the information fast enough and getting across? Do you need more bandwidth? If you're getting better and better resolution, and now you're having to do it in real time, I assume you're trying to suck it through a small straw, and you want to take in more and more, don't you?
It's back to that grid thing or pixels or something. Like I just keep thinking of the metaphor here, right? It's not the earth, like it could be just some 3D rendering of something. And if you're trying to talk about facts about the pixels and about like this pixel is red or this pixel is 95 degrees or something like that. I don't know. It's just this is interesting.
yeah, well, when I started thinking about the fingerprint idea, it all of a sudden there was a lot of other technologies that start to make sense because they're all kind of running on that same idea. Some of the ways that AI works, for example, with picture formation is using those pixels in a similar kind of way and recognizing those little coordinates to bring together the actual meaning of, if you're trying to create a picture of a cow, it's going to go through a lot of pictures, match up things that look like a cow. So it recognizes that pattern, but it is ultimately very similar.
And then maybe when we're saying the data side of this instead of like the data visualization side, right? The data is just lat long or coordinates or whatever, like the point on the grid and the map and the associated facts. And like that's just the data in the raw. But then the processing or rendering engine is picking that up and displaying it however it wants or whatever makes sense logically or physically, objectively.
Yeah, it's a little different process, but yeah, the importance of that grid is definitely helpful in trying to understand what things are doing.
Yeah, very cool. Any other questions for Marcia here? Or just discussion questions for the group?
I was wondering what some good resources might be for the newest news on GIS regarding space, stuff like that, newest tech, that kind of thing, a blog or a website of news or something.
I did see looks like there's a NASA data link in here that was shared. And looks like Daniel also shared something with 3D modeling of the moon with QGIS. There's quite a bit out there. I'm slightly biased to Esri products and, they've done a lot, but I don't know. I think I would explore. I'm sure there's some people in here that know more on that question than I do.
This is where we need Michael Patrick to
Yeah, I
post
know. I was
post
thinking
his
about him.
bookmarks into the chat.
Yeah.
Yeah.
I posted a question into the chat that feels kind of related to this, is what I was saying earlier, is like I remember like the original number wasn't like 6 feet, it was like the accuracy of GIS, and I kind of thought like the original GIS technology was this government technology that allowed a device to know where it was on the planet, roughly speaking, and that I don't know the precision and accuracy of that now, but it became civilian technology long ago, and now devices can have a GIS chip within them that places them and their signals, if you will, like the data that they can throw off. It allows them to tie or stream data that is mappable because it is actively tagged ambiently and automatically because of the GIS signal in the chip, which is tied to a satellite to tie it to a place on Earth or wherever you might be.
Right. Well, and there is still that alignment between that base map, whatever base map is being used,
Mm.
with that signal. So
Mhm.
that's another important factor. A lot of the Esri products now will actually do that alignment automatically, but we used to have to do it manually, and go in there and set the actual Mercator, I forget what it was called. But yeah, there were settings in Esri that we had to make sure we had it right, or it was easy to misdisplay something.
Very cool. Any other questions or discussion questions, comments?
Like Guillermo left a comment talking about struggling with the creative approach to coming up with a project and some ideas that we would be excited to see. That kind of gets my mind churning a little bit in terms of how to explore what your interests are in order to start coming up with questions that you might be able to address with these tools. So I don't have anything on the top of my head other than traveling to Mars and maybe anticipating seismic activity or planetary activity that would be helpful for the safety of the astronauts when they get there or something.
One other thing I'm thinking about here is like just how, at least in my experience, I didn't obviously have a GIS device, a GPS device, and maybe that's another question. Like, what's the difference between GIS and GPS? Maybe that's my confusion here. Does anybody have a quick answer for that? I guess
So,
GIS would be the broad field, and GPS is the signal I'm talking about.
well, GIS is geospatial information systems,
Right.
whereas GPS is the geospatial
Mobile.
positioning
Right,
system.
right.
Yeah.
And they're related, and okay.
Mhm.
Is
Maybe say GPS is a great way to locate yourself
Right,
pretty accurately, darn accurately.
right.
But yeah, but there are other ways to do it too. Your cell towers can locate you. You can measure yourself on a map. You can cite the stars, whatever.
Right.
I posted into the chat a link to last year's Space Apps Challenge challenges, which if you're looking for some ideas to get your gears working on a project related to space data, it's a good place to start.
Just on something that I've been involved in before, in UK, I was with the Zephyr program, which is a high altitude stratospheric unmanned aircraft, so 25 kilometers up. So that's kind of why I'm asking the idea of, if you're getting your resolution already from satellite, do you really need a better resolution from a stratospheric UAV, or is there some other way it can be used? Because there's another player in New Zealand here now doing or attempting to do stratospheric, and having done some experience in developing the payloads for that, I'm interested to see whether you guys are another part of the market that might want a better service. Anyone want to comment on the difference between 500 kilometers up at a low Earth orbit versus being 20 kilometers up, whether it gives you an advantage?
I think part of the advantages come over visit rates, right? if you're able to fly to a particular location at will, it may be easier to do that than to task a satellite. Yeah, sorry, Stan.
No, I was say the same thing. It's basically, you know, the satellite gives you a broad coverage of the whole planet, generally, but the question is how often the revisit is. And but the resolution, you know, typically we're at 30 centimeters today. Maybe the NRO satellites are a lot better, but you know, that's on traditional optical. And if you run VLEO, very low Earth orbit, you can get better. But I'm sure there's got to be, I just don't know what there are applications. If you want your field, if you're in agriculture and you need your field surveyed at a much higher fidelity than you get from just space, you know, it's certainly got to be a lot cheaper to fly a drone than at some price point than to, you know, to get satellite imagery. Although satellite imagery, to Mike's point, is getting a lot less expensive, and they've got so many different modalities now, from optical to thermal to hyperspectral and radar and all kinds of things. So I think it's all very use case specific. The whole space data business for Earth observation is very verticalized, very vertical use cases. The buyers in all of these vertical markets are very unique in their knowledge and needs, and they need to be talked to and sold to in unique ways. And it makes it a very complicated go-to-market strategy, whether you're in airborne, VLEO, LEO, or GEO. You're trying to sell data. There's no killer app. I have yet to see the killer app in this business. So that's the challenge.
Is the issue there kind of like fidelity? I just keep thinking of my basic understanding of the system here is at some level I can only know that I'm in my lawn, but I'm not in a hole in my lawn from space, you know. Do you know what I mean? Like it doesn't know about the divots in my lawn, but something else might, and then that's where I don't know, synthetic aperture radar and things that have higher fidelity. I don't, again, I just am clueless about this stuff.
I think something that came up with Airbus in UK was if we're doing public data and we go to a resolution less than 30 centimeters, you're starting to identify individuals, and then you get into a real issue of, you know, what's that privacy? People are going to really push back if you're saying, well, we can identify you anywhere, anytime.
I thought you
Which we know
already
we
had that
can't.
there on all the traffic cameras and everything.
Hey guys, Marcia, thank you so much. I need to drop for my next thing, but I really appreciate you taking the time. You guys can continue on. Thank you, Eric, for
Thank you, Mike.
hosting.
Good to see you.
Thank you.
Well, Tim, you got another one?
I could keep brainstorming, but nothing off the top of my head.
Okay. Anybody else? I'm probably good personally.
I'm good. Thank you very much. That was fantastic. Appreciate it.
Yeah.
It
Good
kind
job,
of
Marcia.
remotivated me to start studying space data again. Thank you, Marcia.
Thank you for having me. I absolutely love this topic.
Thanks for sharing. Thanks for being here. Have a great night,
Thank you.
everybody. See ya.
See you,
Bye-bye.
folks.
Bye.